Hello, everyone. Thank you for joining the stream. Let me know in the comments where you're coming from, what time it is, where you're at. I'm going to share my screen now, and then we can start. Okay, so let's start. So before we start, my name is Daniele. So most people call me Daniele or Dan, or they make a funny joke and say D5E. That's related to Kubernetes abbreviation. I've been a speaker at KubeCon twice, and I was one of the first 500 certified Kubernetes administrators back in the days when the exam was 3 hours long. That was a real challenge. And what I do is I teach Kubernetes. I run workshops and I create material to help other people just learn and use Kubernetes on a day-to-day basis. And I work for a company called Learn Kubernetes. But today we're going to talk about containers and Kubernetes and how these things work together and why you should pay attention to them. But before we do so, I think we need to go back, take a step back, and basically look at what happened in the past, in the recent past, to software delivery and how we deliver applications. So, in general, back in the days, what we used to do is we used to have large applications, and those large applications were a good idea. That's what was a viable option at the time. But what happened, in sort of a recent past, is that we decided to basically slice and dice those into smaller components, and each component is sort of isolated and focusing on a single function. And we thought this was a good idea, and we do it, to this day as well. We think this is a good idea because we can have deployment which are independent, and so we don't need to wait for anyone else. We can just deliver a unit we can deploy a unit in isolation. Then it's easier to iterate because you're working just on a single component. You don't need to know how the entire system works. And then at the same time, is because of these components can be scaled and plugged in independently. What happens is if one of these components is broken, then that failure is just isolated to that single component. Of course, that might affect the rest of the system, but still there is some sort of isolation in the failure as well. So we thought, well, this is great, right? We went from something which was really big to something which is smaller and manageable. But let's have a look at what happened in infrastructure. So when you look at the infrastructure, then we used to have virtual machines running those applications. And now what we're doing is we're basically breaking those down and having to run smaller applications. Of course, you don't want to run those smaller applications and sharing the same virtual machine. You might want to have like a dedicated virtual machine for each of those. And here comes the challenge. The first challenge is when we used to have like a single virtual machine with a single application running, then what used to happen is that there was an operating system. There was an operating system that was using resources on that virtual machine, and the rest of it could be used by the application itself. Those virtual machines tend to be bigger, so the ratio between what was used by the operating system or any other third-party software was quite small, so 2 to 3%. But when we focus on microservices, just on smaller services, then what we notice is that those services tend to use less resources than its predecessors. So what happens is the ratio between what is used by operating system and system daemons or any sort of other process which is necessary to run the virtual machines, then the ratio is slightly different. And then in this particular case, we're basically talking about an overhead. So things that you need to run in order to run these virtual machines was 6 to 10%, which basically means that you're spending a lot of money on resources that you need to run, but you don't really want to. So how can we get rid of those? And the second is, so these services that we build, they are not necessarily all the same. They actually come in different shapes and sizes. And what do I mean by that? So if you think of it, when you develop an application, that application might be like CPU intensive. Perhaps you're executing, you're performing some calculations, and so you're using all the CPU you've got to produce the result. Or perhaps you're running an application which is, perhaps encoding video, and you need more memory to process the frames. So bottom line is that these services that we build, they come with different sort of requirement. And if you have a single virtual machine or a set of virtual machines that you can use, then what you usually do is you just deploy that in a virtual machine and then you move on. The issue is that virtual machines have got a fixed allocation of resources. So if the virtual machine has got 4 GB of memory and 2 CPUs, if you only use a fraction of it, then the rest will be underutilized. Now, you might be a little bit luckier, and some of the applications might use most of the resources, but still there is this gap. There's all of these resources that are potentially wasted. But what if we could break free of those and actually run all of these processes without the overhead of this fixed allocation? Before we get to the answer, we also need to explore how we used to package those applications and how we used to deploy in virtual machine. So if you have an application which is built in Java, like Spring Boot, for example, you had to pre-provision the environment with the JVM and perhaps some external libraries as well. If you used to run Node.js, you had to basically create a virtual machine, install Node.js, and perhaps install also dependencies like Python or tool chains. And once that was done, then you had the opportunity to run the scripts, run your jar, and then execute the application. That was like some challenge. There were some challenges in doing so, and the challenges comes from the fact that a virtual machine isn't particularly fast to boot. On top of that, you had to provision the environment with something like Puppet, and then when the environment is provisioned and you've got a JVM running, then that is the time where we actually bootstrap the application and launch it. So the overall process was quite long. So each and every company had, or still has, sort of their own ways to manage these pre-provisioning the environment. Some people might take screenshots. Some companies might take snapshots of those VMs and then save them for later use. And then what they would do, they would basically run from snapshots, which would save them some time during the provisioning phase, and then running the application. So in essence, there wasn't really a standard way to take these snapshots, to reduce this time for reconfiguring environments, for just managing this number of virtual machines and environments. So what's the solution? Well, first of all, we need to realize that actually virtual machines are good. I mean, we use them because they offer us isolation, because they offer us a way to limit the amount of resources that can be used by the application that is deployed inside it. And they limit sort of what other processes can do with it. So they're good for multi-tenancy as well. But is it the only technology that is offering this kind of trade-off? Well, it turns out that we can emulate, we can sort of get closer to it by using the kernel, the Linux kernel. So when your application starts and wants to send some messages over the network, of course, it doesn't actually go and send these messages by itself. Instead, what it does, it basically uses the kernel as an API and basically tells the kernel, hey, can I please send this network packet using your network card on your computer? And then the kernel will basically use the driver to send those messages, right? The same happens for things like files, for example. If you want to access your hard drive, you don't access it directly. You just send a message. You send an API call to the kernel, which is basically going to give you access from that. So these API calls are called syscalls, and basically everything goes through the kernel, right? That's how it works. So what if we could actually, if you imagine the kernel like being an API, what if we could actually limit what kind of things you can do with the API? And the idea of control groups is basically to say, okay, some APIs you're only allowed to use, a certain amount of it. And for example, you could say, For this group of processes, or for these processes like the JVM, I just want to allocate some memory and some network, some bandwidth and some CPU. And then you could do the same for other processes as well. And what you're doing basically is you're just segmenting how much this API can be used and how much of these resources can be utilized by the application. That was the first one. And then the second one is called namespaces. And namespaces, what they do is basically they isolate what you can do. You can think about like a way to scope what kind of API calls can be called on the kernel. So for example, you could say, okay, I want to scope. So for example, what you can do, so Linux namespaces are like several namespaces, and one of them, for example, is dedicated to network, so you can isolate network. Another one is the mount namespace, which is presented here. And with the mount namespace, what you can do, you can say, okay, I'm going to create a folder on my computer, and then I'm going to tell the application that this is the folder, and this is the folder that contains all the file, like if it were to be a root. Right. So a full copy of what you will find in Linux file system then is available under this nested folder on my hard drive. So the process believes that it has full access to the hard drive, but in reality, it's just basically a subfolder somewhere else. So these namespaces actually, they help me with isolation, and control groups, they help me with scoping how many resources are assigned to processes. So it turns out that these two features, Linux kernel features, are quite handy, but they're quite very low level, and they're a little bit hard to use on a day-to-day basis. So someone basically built abstraction on top of those to make them more user-friendly, and that's basically when we got tools like Docker. So Docker, and you might have heard of other tools like Podman, for example, they pretty much do all the same thing, which is basically just nicer way to interact with containers and creating these sort of limits to this API. So Docker is the good example. You might find other container runtimes as well. Now we've got this application deployed, and this is already a massive progress. A massive advantage if you think about it. If before, if you had 3 applications, you had to go inside the virtual machines, provision 3 environments, and keep them up to date, right? You had to be aware of what kind of applications were deployed inside the server. But now, if you compare that with Docker, what we do is we actually package each application into a container. And then instead of running the application itself, we just do run the container, run the container, run the container. We don't really mind what's inside the container. The only things we care is that we're running the container. And that's good. It's actually easier to reason about. But there are some challenges, and the challenges are, okay, I've got a lot of containers now. How do I actually make sense of them? How do I actually distribute the allocations of the containers? Do I need to keep track of where I deploy things? The other question, and does it actually scale if we've got several servers? And the other question I've got is, okay, if those containers are connected, and that's good, what happens when I've got like several nodes? How are those connected? How is the network between these nodes linked? And Docker doesn't provide, the Linux kernel doesn't provide any cross-node networking. So Linux containers cannot help us here. So what do we do here? So it turns out that these problems, so I don't know if you noticed, but all the problems that just came out when we started scaling from a single computer into several. And so what we need is basically to go back and just treat everything as a single entity, as a single computer. And then ideally we want something that helps us to allocate these containers at runtime. And ideally also programmable. It turns out that these kind of problems is solved by a set of tools called containers, orchestrators. So a good example, of course, is Kubernetes, hopefully what you hear today to learn more. And it's also not a fair fight. When it comes to adoption, then Kubernetes is the de facto winner. So how does this Kubernetes work? So generally you have a collection of servers, like I showed you before, and then you basically select one, you say, okay, this is going to be my control plane. And the control plane is basically the brain of Kubernetes. The rest of the nodes will basically join as working nodes, And then once you create this cluster, then it behaves like a single unit. So if you say, I want to deploy a container, then you just deploy the container to the cluster itself. And then under the hood, what you will see is that all of these containers will basically be allocated to different nodes. Okay, this is basically where Kubernetes will decide where to place the nodes. So when it comes to resources, then Kubernetes will look at these worker nodes and basically find, aggregate all of the resources available. So like CPU and memory will just basically, the cluster will have the aggregate CPU and memory of all of the nodes. Doesn't matter if they're big or small or different sizes, it will just be aggregated. The other things that will happen is that, we talked about how these microservices sometimes have got different resource requirements. They might have CPU, they may need more CPU or more memory. So in general, what happens is Kubernetes will basically help you to allocate these containers inside a node. And what it will do, it will basically find a way to, it will basically receive your suggestion on how big it is, and then we'll try to place it inside the infrastructure. And when I say place it or allocate it inside the infrastructure, if it looks like Tetris, yeah, it's mostly, it's a little bit more complicated than that, but it is more like playing Tetris. So Kubernetes will basically play Tetris with your infrastructure and try to fit as many containers as possible in those nodes. Of course, there are other parameters that Kubernetes will keep into consideration, but overall, that's basically the idea. We'll just basically do the work of figuring out where this block should be placed. And the third one, which is quite interesting, is that this Kubernetes basically is a collection of APIs that sits on top of a real infrastructure. So when you deploy these workloads are deployed on Kubernetes and not on a cloud provider. So if you were to switch or use on-premise, then you can use the sort of same set of constructs and object. The only things you need to do is basically just change the underlying layer. Yeah, sounds simple. Well, it's a little bit more complex than that, but hopefully you got the idea of how Kubernetes works. Now, let's get to business and let's have a look at how you actually deploy something into Kubernetes. So let's imagine that you've got a red page, which is written, in, I don't know, it's a Go application that just displays a red page. And you want to deploy that application because users are going to visit it. So ideally, what you want to do is you want to wrap this into a container, and you want user to come and visit the container and just consume the application. However, what happens when the application becomes popular? You might need to scale it, right? And you might need to create more instances. And this is for maybe the first challenge. So how do we, in the previous way of doing things, right? Before Kubernetes was a thing, what did you do to actually distribute the traffic, to balance the traffic between these two instances? You might have used a load balancer. A load balancer is a strategy to actually distribute the connection between two applications. But there is another sort of challenge here, which is, okay, what if I've got two different types of applications? So we talked about how, breaking a monolith into smaller components is leading to a proliferation of apps. So you might need more applications deployed in the same cluster. Well, we need a way to route this traffic from one application to the other. So what could we do? What you could do is have like another load balancer on top, and this time this load balancer is slightly different. It will basically route the traffic from one. It will basically decide where this traffic should be routed and what kind of internal load balancer will need to receive it. So it turns out that this is quite straightforward. You've probably seen this in the past, and just using virtual machines and load balancers. In Kubernetes, we use the same structure. The only difference is that we call the internal load balancers, we call them services. The external load balancer, we call it an ingress. And we don't call the applications containers or applications. We call them pods. And on top of this, there is something else that you don't see, is that we don't actually deploy pods in isolation. Instead of what we use is basically a resource called deployment. And a deployment is basically we define a template of what an application looks like, and then we just tell Kubernetes, please, I want 3 copies of it. And what Kubernetes will do basically will create the 3 copies and it will watch over them. So if something happens to one of them, it's going to recreate it. Time for a demo. Yeah. Okay, so I've got. So before we start, I'll actually show you what a deployment looks like. Let me just show you what I've got locally. I've got I'm running Minikube, which is a Kubernetes local cluster. It's running locally, so hopefully no surprises. And then the other things we talked about containers. So most of the time when we talk about containers, we talked about how something you can actually touch, like a real container. But in reality, containers are not such a thing. Containers are basically just a way to isolate the process and define some sort of restrictions on what kind of things can see and how many resources can use. So I think the best way to actually see what a containers look like is not to build one, but to actually inspect an existing one. So what I'm doing here, I'm basically just saving the container as a tar file. And what I can do, I can just open it and I can see the engineer tar file here. So I can just decompress it and go inside. And I don't know if you can see, maybe like this. Okay, I don't know if you can see, but there are several folders. And inside each folder, there are basically more files. And in each folder, there is basically a layer.tar, a JSON version, and so on and so forth. Those are basically what we call layers. So a container is actually divided into layers. And then I'm going to pick the biggest one, which is, I think, this one. I'm going to unpack it. And if I go and look inside, there is another layer folder. And there is a folder, and basically, there is like several folders which look like a Linux file system. That's because it is. So what this container is basically just a collection of files plus some extra metadata, plus some extra way for running the process. So if I dig, this is an Nginx container. So if I'm lucky enough, I should be able to find the Nginx binary somewhere in one of those layers. Now, I'll leave that to you as an exercise for the reader. But that's what a container looks like. Now let's go back to Minikube. We want to deploy an application. So what I've got for you is this very long YAML file and a few others. Now, let's not focus too much about what they are. I'm just going to show you how they are deployed, and then we can take it. We can discuss it a little bit more. So I'm going to deploy the application. To do that, I can just use kubectl apply deployment. kubectl apply service. kubectl apply ingress. Okay, so there is one thing I want you to notice is that I basically, I've got some files. We will look into what they are, but as soon as I basically ask Kubernetes to deploy them, then there is no waiting time. Kubernetes the command is just accepted immediately. So Kubernetes is basically saying, yeah, done, I'm going to do it. Yeah, whatever. We'll see. So if I go and load the page, yeah, I can see that the page is live now. It's version 1. Excellent. And if I do a command kubectl get pods, I can see that there is one pod, so one application running, and it's been created 48 seconds ago. So I just created the application. Let's have a look at what kind of files are used for that. So the first one is called deployment. So we described the deployment as something like a template for pods where can they be just copied. And you can see the word template here because that is exactly how it works. Kubernetes will basically look inside the structure and basically say, oh, you have a container. Let me create one copy of it. So what happens if I change this to 5 copies? Well, let's say 3. And I do a kubectl apply the file I just changed. And I do kubectl get pods. Then I can see that there are 2 more pods running in my cluster, which is great. So basically Kubernetes will look at this and create more copies based on the instructions that you see here. And we talked about how Kubernetes looks after these pods. Does it? So let's have a look and try and delete one. So I'm going to delete this one, and we're going to check the age column to see what happens next. Yeah, I can see it has been deleted, and Kubernetes replaced it with another one. So it actually works. So Kubernetes will create another pod as one is deleted. Excellent. So the other two files are the service, which is the internal load balancer. So you can see here the name is service, and then it's basically specifying some ports. So that's usually just the port exposed and the port that's been consumed. We've got an extra port here, which is for debugging, basically. Yeah. And then the ingress is more like a programmable router, I would say, for routing traffic into the cluster. So in this case, I'm saying all the traffic that go to /, please send it to the service, which in turn is going to send it to the pods. That's how it works. Cool. Let me get back to my slides. Let's play with something else now. So the other things that is quite interesting and comes out of the box with Kubernetes, and you might use quite a lot, is something called rolling updates. So most of the time, we don't just deploy an application, we deploy several of them with changes. And ideally, we want these deployments to go smoothly. We want to deploy a new version, but we don't want to stop the service and then deploy and then resume operations, right? We want to do everything at once. And Kubernetes has got a native way to do that. And that's basically just by changing the version of your container, then Kubernetes, what it will do, it will basically detect that your intention is to roll out a new version of your application. And what it will do, it will basically create a new pod, it will remove the old one, and then create a new pod, remove the old one, create a new pod, and then remove the old one. This is called a rolling update because you're progressively rolling out a newer version of your application. Let's have a look at how it works. So I deploy the application. So if I go back to the terminal and I do a curl on localhost /version, then we should be able to see the version of this application deployed, which is version 1. So what I can do is I can set a while loop, which is going to curl this version every half second. And you can see here that version 1 is actually the version that's been returned by the application. Okay, let's go back to the YAML file and change the version to versions 2. And now we're going to try and submit this resource to the cluster and observe what happens to deployment. Let's go back quickly. So I can already see some versions 2 popping up. But you can see the majority of the traffic for version 1. Now we've got few versions 2. And then as time goes on, there is a mix of 1 and 2. And then if I wait long enough, then it will fully transition to version 2. And I can see the transition here. So what I've done, I basically just changed the image. So the image, the container image is basically, imagine you have created a new version of your application, and then you decided it was time to deploy it live. And you just changed the version in your deployment of YAML. And then what happened is Kubernetes will orchestrate this rollout where progressively traffic was reduced from the previous version of the application and then increased in the current version. That's how it works. Excellent. So is that it? Is that Kubernetes? Is all you can do? Well, I think it's a complicated question. So I think most of the things that you would like to know about Kubernetes is that, deployments are a big part. Being able to restart applications that are not healthy and being able to distribute them across several nodes, it covers most of the use case of Kubernetes. But of course, there are more. If you want, you can basically define ways for your application to scale. So for example, you might say, I want to scale my application based on the number of messages in a queue or the traffic that I'm receiving via the ingress, for example. You can do that with something that we call the horizontal pod autoscaler, which is basically just a fancy way for saying, as you receive more traffic, please create more pods. in the same way you've seen me do changing the replicas in this file, then you can do it automatically with Kubernetes. But what happens when the cluster runs out of space? Well, here's where Kubernetes is composed can be basically extended. So there are other components you can install, which is basically going to automatically create a new node when the cluster resources are running low, and that will basically give you more opportunity to actually combine it to do and basically scale the number of pods, scale the number of nodes as you increment the number of replicas in your cluster. And of course, why stopping in a single cluster when you could combine several of them together. So you could send like a message to one Kubernetes cluster and have like several other Kubernetes clusters being deploying other applications around the world in a sort of orchestrated fashion. So I think what the major takeaways from these is that, first of all, we had a look at containers and how these containers are basically just an easy way to basically package applications, share them, and then define requirements and sort of constraints that we want to apply to them. And at the end of the day, you saw it when I untagged the file. But what containers are basically just processes at the end of the day. Then we had a look at the challenges that we have with a proliferation of containers, and how do we manage this network to span several nodes, and how do we manage allocations? So this is basically the orchestration layer. This is basically where Kubernetes shines. And then we had a look at resources like deployment, ingress, and services. Of course, Kubernetes has got more resources. You might be interested in things like storage, for example, or a way to segregate resources or to logically group them together. But ideally, I think the idea I want you to take away from this is that Kubernetes provides a unified API through YAML files where you can basically define resources and how they interact with each other or don't interact with each other. And then we had a look at this rolling update and also scaling. And I think this is basically where we see how Kubernetes can be designed and extended to actually fit different use cases and unique use cases that go from things like deployment, scaling, but there are also ways to do, for example, backups and disaster recovery, or it can be sort of customized to do pretty much anything you want. Yeah, that's pretty much all I wanted to show you today. Thank you very much for tuning in. I hope you enjoyed. I hope it was useful. If you like this, we're running more courses. All of this material is based on the courses that we do at Learn Kubernetes. So I think you should check them out. This is something you're planning to do. And the other things if you are into Kubernetes, want to keep up to date with resources and tutorials, then I publish a newsletter every week with the best resources to learn. So I suggest signing up for those as well. I left the link in the description. But yeah, that's all from me. I don't really know how the chat works and the Q&A, but if you've got a question and it's in the chat, I'll be happy to answer them. Excellent. No more questions. So I think this is the end. Thank you very much for tuning in. I hope you enjoyed.